Hi, my name is Ali Baghani and I'm a research scientist at Ultrasonix Analogic Ultrasound. Today I'm going to give you an overview of Ultrasonix's internal system architecture. This is how I've organized this presentation. First, I'm going to talk about the flexibilities of our system architecture. Then I'll move on to the exam software, which is the main imaging software which runs on our systems and is used by both the clinicians and researchers to acquire ultrasound images. I'll also talk about the software development kits or SDKs that we provide with our systems so people can interface with our software and develop their own custom code to run on our systems. I will go into the details of how our systems perform pulse ultrasound imaging and the internal software structures that are used to support this kind of imaging. Then you'll get an overview of the hardware on our systems, and I'll finish by a few slides about our transducers. Ultrasonic systems have a flexible design architecture which, in addition to conventional ultrasound imaging modes, makes it possible to develop new imaging modes and do research using these platforms. Ultrasound imaging is generally divided into two categories: the continuous wave ultrasound and pulse wave ultrasound. The continuous wave ultrasound has a limited application, whereas most of the conventional ultrasound imaging modes which are regularly used in practice are pulse wave ultrasound. These include M mode, B mode, pulse wave Doppler, color Doppler, harmonic imaging, and techniques such as spatial compounding and duplex and triplex. Ultrasonics design flexibilities. First of all, ultrasonic systems are PC-based. This has made it possible for us to reduce the form factor or physical size of our systems, especially compared to the older systems which used dedicated hardware. Moreover, it is possible to easily tap into the parallel processing power of GPUs, which are becoming commonplace today, for advanced image processing at a low cost. We use Windows XP as our operating system, and this has made it possible to program the system in familiar environments such as Visual Studio and MATLAB. On the hardware side, we use a lot of programmable hardware such as FPGAs, which makes it possible for us to incorporate design improvements and new features as upgrades to the firmware. These can easily be distributed as software updates for the system and provide a great flexibility on the hardware side. Not only do we use programmable hardware, but also the firmware itself is highly parameterized. That means it is possible to adjust all of the imaging parameters through software. This makes it possible to adjust and improve the imaging through the software. Moreover, the same hardware can be used to implement novel imaging methods. The software was also designed with an emphasis on flexibility. All of the imaging parameters are defined and stored in XML files. This makes it possible to read and edit the values of the parameters outside the programming environment using text editors. Also, researchers and OEM customers can access the parameters and change their values without the need to modify the core code of ultrasonics. After the short introduction, I will now move on to the exam software. The exam software is the main clinical software that runs on ultrasonic systems and is used by clinicians for ultrasound imaging in their practice. As with any standard imaging system, the exam software provides conventional imaging modes such as B mode and Doppler imaging. In addition, with a research license, it is possible to access the raw data as well as processed data acquired by the exam software, either in real time or to save it to the disk for offline processing. In the following slides, I'll go over the basics of the exam software. The exam software, when used by clinicians, gives them the standard flexibility in adjusting the imaging parameters such as the depth of imaging and number and loci of focus points. These are standard parameters that clinicians are accustomed to adjusting when they do ultrasound imaging in order to do their ultrasound examination. The software is FDA approved, and we have approval in other jurisdictions as well. The adjustment of parameters in the clinical mode will not pose a risk to the patient, and the output ultrasound energy is always within regulated limits set by these authorities. However, with a research license, the exam software can be switched into a research mode. In the research mode, the user has extended control over almost all the imaging parameters used in the software. The research mode is not an FDA or other jurisdiction approved software. It is the responsibility of the researcher to ensure the safe operation of the machine in this mode. The research mode gives access to raw data as well as other forms of processed ultrasound data from the exam software. Pulsed ultrasound. As I mentioned earlier, I will focus on pulsed ultrasound imaging as it is the most common way of ultrasound imaging. In pulsed ultrasound imaging, an electrical pulse is applied to the ultrasound transducer. This pulse has a short duration, usually one or a few cycles. The transducer converts the electrical pulse into a mechanical pulse. The mechanical wave propagates through the tissue and generates echoes which travel backwards towards the transducer. These returning echoes are picked up by the transducer and converted into an electrical signal which is called the RF signal. The ultrasonic systems have a number of adjustable parameters that affect the transmitted pulse and received RF signal. In the next couple of slides, I will go over these parameters. There are a number of adjustable parameters that can be used to design the shape of the electrical pulse that is applied to the transducers. This is usually called the transmit pulse. However, the flexibilities have some limitations too. Our systems do not have digital to analog converters on the transmit channels, and therefore it is not possible to generate arbitrary shaped signals as one could do, for example, using a signal generator and send them to the transducers. The shape of the electrical pulse that is applied to the transducers is always a square wave shape. Think of it as a digital signal that has been amplified to tens of volts. The shape of the square wave can, however, be adjusted by changing the shape of that digital signal. Note the actual shape of the mechanical wave will be more a sinusoidal shape. This is because ultrasound transducers have a limited bandwidth, and when they convert electrical energy into mechanical energy, they act as a bandpass filter. Therefore, the sharp edges of the electrical pulse we apply to the transducer will inevitably be smoothed out, and a more or less sinusoidal mechanical wave will be transmitted inside the tissue. This is the main reason why we never bother to use more sophisticated hardware such as analog to digital converters for transmit.